631,000 years ago, the ground beneath what is now Wyoming cracked open along a ring of fractures 40 miles wide. Within hours, columns of pulverized rock punched through the stratosphere. Within days, a gray blanket of glass shards was falling on a continent that had no name, covering a footprint stretching from the Pacific coast to the Gulf of Mexico. This is the story of what the Yellowstone hotspot did the last time it fully let go, and of the physical mechanisms, not the mythology, that made it the most destructive geological event in North American history. The eruption did not begin with a single explosion from a central peak. There was no peak. The crust above the magma chamber had been swelling for centuries as pressure built below, and when it finally failed, it failed along circular fractures called ring faults, cracks that propagated outward in a widening arc across the landscape. The moment those faults reached the magma chamber, the pressure differential became catastrophic. Rhyolitic magma under enormous confining pressure does not flow out of an opening. It decompresses. In the fraction of a second after the ring faults breach the chamber, the dissolved gases inside the magma, water vapor, carbon dioxide, sulfur dioxide, expanded instantaneously, shattering the magma itself into microscopic fragments of volcanic glass and launching them upward at velocities that carried material past the troposphere and into the stratosphere. Multiple Plinian columns, named for the Roman writer who documented Vesuvius, rose tens of miles into the sky simultaneously. They are not columns of smoke. They are supersonic jets of fragmented rock, gas, and ash, self-sustaining as long as the eruption continues to feed heat from below. From a sufficient distance, they would have looked like immense dark towers connecting the ground to the upper atmosphere. The columns did not hold. As they grew denser and heavier, the upward thrust could no longer support their weight. They collapsed. Collapsing columns generated pyroclastic flows, avalanches of superheated gas, ash, and fragmented rock that raced outward from the vent zone at speeds exceeding 200 miles per hour, at temperatures above 1,000 degrees Fahrenheit. These flows incinerated and buried everything within roughly 100 miles, filling valleys and overrunning ridgelines, laying down massive sheets of ignimbrite. The solidified rock formed when a pyroclastic flow cools in place. The final act was the caldera collapse. The shallow magma chamber had expelled enough material that the rock above it lost structural support. A section of the North American continent, a chunk measuring roughly 34 by 45 miles, dropped thousands of feet into the emptied space below. That depression is the Yellowstone Caldera. The tourists walking the boardwalks above the Grand Prismatic Spring are standing on its floor. 1,000 cubic kilometers of material left the ground during this event. The 1980 eruption of Mount St. Helens ejected approximately 1 cubic kilometer. The Lava Creek eruption was 1,000 times larger. To understand why the Lava Creek eruption happened where it did and why it was so violent, it is necessary to go deeper, both in space and in time. Beneath Yellowstone, at depths reaching into the lower crust and upper mantle, sits a mantle plume, a column of superheated rock rising from near the boundary between Earth's core and mantle. The plume does not move. The North American plate above it does, drifting southwest at roughly an inch per year. The result is that the plume has been burning through successive sections of the continent for approximately 16 million years, leaving a 500-mile trail of destroyed and reshaped landscape across what is now Idaho. That trail, visible today as the flat basaltic depression of the Snake River Plain, is a sequence of ancient, overlapping volcanic calderas, each one marking a previous position of the same hotspot. Yellowstone is not a geological anomaly. It is the current address of a process that has been operating continuously since the Miocene. The plumbing system beneath Yellowstone is two-tiered. Rising from the plume is basaltic magma, hot, fluid, and relatively mobile. It pools in the lower crust. The intense heat radiating from this basaltic reservoir bakes the continental crust above it, melting it into a secondary magma body much closer to the surface. This secondary reservoir is filled with rhyolitic magma, and rhyolite is key to understanding the violence of the Lava Creek eruption. Rhyolite is extraordinarily viscous, Where basaltic magma flows like hot water, rhyolite behaves more like cold tar, thick, resistant, and incapable of moving quickly. This viscosity has one critical consequence: it traps gas. As volcanic gases bubble upward from the mantle into the shallow rhyolitic reservoir, the magma is too thick to allow them to escape gradually. The gas dissolves into the melt under pressure and stays there. Over thousands of years, the concentration of dissolved volatiles in the magma increases. The pressure mounts. The crust above deforms upward as the chamber inflates. A basaltic volcano relieves this pressure continuously, bleeding lava at the surface. A rhyolitic supervolcano cannot. The viscosity of the magma prevents any gradual release. The only outcome, when the structural integrity of the overlying crust is finally exceeded, is explosive decompression. The Lava Creek eruption was not an unusual event for the Yellowstone system. It was the system behaving exactly as its physics dictate. The pyroclastic flows destroyed the landscape immediately surrounding the vent zone. The continental catastrophe was carried on the wind. The eruption columns that punched into the stratosphere delivered pulverized rock across a footprint spanning most of modern North America. Geologists call this material tephra, fragmented volcanic ejecta distributed by air. The specific deposit from the Lava Creek eruption is known as the Lava Creek Tuff, and its traces have been recovered in sediment cores drilled from the bottom of the Pacific Ocean and the Gulf of Mexico, demonstrating that the atmospheric distribution was hemispheric. The word ash is misleading. Volcanic ash is not combustion residue. Under a microscope, a sample of the Lava Creek Tuff looks like broken glass. Jagged, angular shards of solidified volcanic glass and microscopic pumice fragments with razor edges. It is abrasive, mildly corrosive, and heavy relative to its volume. Close to the eruption, across Idaho, Montana, and Wyoming, the ashfall accumulated to depths of several feet, collapsing the branches of large trees and crushing rock overhangs under its weight. The region would have been in total darkness for days. Further out, Nebraska, Kansas, the Texas Panhandle, the fall was thinner but still measured in inches, and even a few inches of volcanic glass triggers a cascade of biological failures. The first mechanism was respiratory. For any animal caught in the ashfall, breathing meant inhaling microscopic glass shards. Those shards lacerate the soft tissue of the lungs. The body responds by producing mucus, which combines with the ash to form a dense, cement-like material in the airways. Animals suffocated from the inside. The second mechanism operated through water. Volcanic ash does not dissolve. When it fell into rivers, lakes, and standing water across half the continent, it transformed those water sources into toxic slurry. The Lava Creek magma was enriched in fluorine and sulfur, which leached rapidly into contaminated supplies, poisoning them within days. The third mechanism was photosynthetic. Ash coated every leaf surface across the ashfall zone, blocking sunlight from reaching chlorophyll. It also destroyed the waxy cuticle layer that protects plant leaves from desiccation. Plants began dying within weeks, not from heat, but from suffocation and dehydration. The fourth mechanism was the slowest and the most inescapable. Fluorine from the ash leached into soil and was absorbed by surviving vegetation. Animals that ingested fluorine-laden plant matter developed osteofluorosis, a condition in which excess fluorine causes abnormal bone growth. Painful bony outgrowths called exostoses form on the skeleton, progressively restricting movement. Animals that had survived the immediate ashfall, the contaminated water, and the initial starvation were still dying months later, their bones deforming around them. Grazing herbivores faced a fifth problem specific to their anatomy. Volcanic glass acts as a powerful abrasive against tooth enamel. Any animal that continued chewing ash-coated forage was grinding its molars down to the nerve. The grass was still there. The water, in places, was still there. The food chain was intact in outline while failing at every point of contact. The ashfall was a regional event. The volcanic winter that followed was global. The distinction matters mechanically. Ash particles, the glass shards and pumice fragments, are relatively large and heavy. They begin falling out of the atmosphere within days to weeks of an eruption, settling under gravity. The stratospheric insult that drives a volcanic winter comes from something else: sulfur dioxide gas. The Lava Creek eruption injected massive quantities of sulfur dioxide into the stratosphere, the atmospheric layer above 30,000 to 50,000 feet, above the weather systems where rain would otherwise wash particulates out within days. In the stratosphere, sulfur dioxide reacts with water vapor to form droplets of sulfuric acid. These droplets are extraordinarily small, light enough to remain suspended for years, and they spread across the globe via high-altitude winds. A sulfuric acid aerosol veil is highly reflective. The droplets intercept incoming solar radiation and scatter it back into space before it reaches the Earth's surface. The planet dims. Land surfaces cool. Global average temperatures may have dropped by 5 to 10 degrees Celsius, 9 to 18 degrees Fahrenheit, sustained across several years. The persistence of this veil, well after the eruption itself had ended, is what distinguishes a volcanic winter from a simple weather event. 5 degrees of global cooling does not sound catastrophic until its consequences at the ecological level are mapped. The monsoon systems that drive seasonal rainfall across the tropics depend on the intense summer heating of continental land masses. Cooled continents drive weaker monsoons. Regions dependent on monsoon rainfall experienced multi-year droughts during the volcanic winter following the Lava Creek eruption. In temperate latitudes, the cooling caused unseasonable frosts during spring and summer. Plants that had survived the ashfall and were beginning to recover found their growing season cut short by freezes arriving months too early. The base of the food chain, the primary producers, the grasses and shrubs and trees, was suppressed across the globe simultaneously. The eruption at Yellowstone was a North American event in its immediate physical violence. The volcanic winter it triggered was planetary in its reach. The sulfuric acid aerosol veil does not respect geography or hemisphere. The same mechanism that smothered incoming solar radiation over Wyoming also dimmed sunlight over Central Africa, over Southeast Asia, over the steppes of Central Eurasia. Every ecosystem on Earth was operating on reduced energy input for years after the Lava Creek eruption. To make the mechanisms of the previous 2 chapters concrete, it is necessary to populate the landscape with the animals that experienced them. 631,000 years ago, North America was in the Irvingtonian, a period of the Pleistocene epoch defined by the fauna then living on the continent. It was a world that shared broad outlines with Africa today, but was stocked with animals no living human has ever seen. Columbian mammoths stood up to 13 feet at the shoulder and weighed several tons. Their survival depended on consuming enormous quantities of grass and browse daily. When the Lava Creek ash coated the grasslands of the American West, mammoths faced the dental trap in its most complete form. Molars large and complex enough to grind tough vegetation, but not glass. The volcanic glass stripped enamel faster than the tissue could compensate. Animals that continued feeding ground their teeth down to the nerve in weeks. Starvation followed. Alongside the mammoths were stegomastodons, stockier relatives of modern elephants, and vast herds of camelops, the giant North American camel, and multiple species of early horses. All were bulk grazers or browsers. All faced the same dental destruction and the same fluorine poisoning working through vegetation and water. The predators that hunted these herds responded to the initial kill-off in a way that was, briefly, advantageous to them. Smilodon, the saber-toothed cat, with upper canines reaching 8 inches, was built for large prey. Dire wolves hunted in packs across the same landscape. In the weeks immediately following the eruption, as herbivores died in large numbers, predator populations likely experienced temporary food surplus. The trap closed slowly, as herbivore populations crashed, from suffocation, dental failure, fluorine poisoning, and starvation under the volcanic winter's suppressed food base. The prey biomass that supported Smilodon and the dire wolf disappeared. A predator specialized for large game cannot pivot efficiently to smaller prey. The carnivores that had briefly feasted on the dying followed them into collapse. Giant ground sloths, such as Paramylodon, which used massive foreclaws to pull down vegetation, and the armored glyptodonts lumbering through woodland edges, were affected differently, but no less fatally. Glyptodonts were heavily built and slow-moving. Their armored shells weighed hundreds of pounds. They could not outrun ash clouds or migrate from contaminated zones quickly. Their food sources rotted or were buried under the growing gray blanket. The Irvingtonian fauna was not entirely destroyed. Species survived in refugia, areas outside the heaviest ashfall zone, particularly in the southeast, and where prevailing winds had deposited less material. From these refugia, populations expanded back across the continent over thousands of years as the ash weathered, soils recovered, and vegetation returned. The Lava Creek eruption killed individuals and local populations across a continent. It did not immediately drive species to extinction. What it demonstrated was the capacity of a single geological event to compress the operational margin of an entire ecosystem to near zero, simultaneously, across millions of square miles. For most of the 20th century, the scientific community knew that Yellowstone sat above an immense source of geothermal heat. What it did not know, could not know from the ground, was the true nature of the geological feature responsible. The problem was scale. Geologist Bob Christensen spent years in the 1960s trying to map the volcanic history of the Yellowstone region. He could find evidence of volcanic activity everywhere: lava flows, hydrothermal alteration, ash deposits. But he could not locate the structure that had produced them. The expected feature, a volcanic cone or a visible crater, was absent. Christensen eventually obtained high-altitude aerial photographs taken by NASA for an unrelated survey program. From altitude, the answer became obvious. The entire central plateau of the park, approximately 1,500 square miles, was the caldera. Christensen had been conducting fieldwork inside the crater without recognizing it, because no perspective available from the ground revealed a feature measured in dozens of miles. This discovery established the framework for understanding Yellowstone as a supervolcano, and it set off decades of investigative work to characterize the system, its history, its current state, and its future behavior. Dating the Lava Creek eruption precisely required argon-argon dating, a radiometric technique that exploits the decay of potassium-40 into argon-40. When volcanic magma crystallizes, it traps potassium, but contains no pre-existing argon. The heat of the eruption drives off any argon present before the rock solidifies. From that point, argon-40 accumulates at a known rate as potassium-40 decays. By isolating sanidine crystals, a mineral common in rhyolitic deposits, from the Lava Creek tuff, heating them with a laser to release the trapped argon, and measuring the ratio of potassium to argon with a mass spectrometer, geologists can calculate the elapsed time since crystallization. Recent refinements in this technique revise the eruption date from the previously reported 640,000 years ago to the current figure of 631,000 years ago. The event is not being reinterpreted, it is being measured more precisely. Connecting ash deposits across the continent to the Yellowstone source required geochemical fingerprinting. Volcanic ash has a compositional signature, a specific distribution of trace elements, including titanium, iron, and rare earth metals, that is unique to a given eruption. Ash sampled from a road cut in Nebraska can be matched to the Lava Creek eruption by comparing its trace element profile to reference samples from Yellowstone. This same technique identified Lava Creek ash in deep-sea sediment cores from the Pacific Ocean floor and the Gulf of Mexico. Those cores represent a continuous archive of atmospheric fallout stretching back millions of years, layered in fine increments that geologists read like pages. The current state of the magma system beneath Yellowstone is visible through seismic tomography, a technique that uses seismic waves generated by earthquakes to image the interior of the Earth. Seismic waves travel at different speeds depending on the temperature and composition of the material they pass through. Hot, partially molten rock slows them. Cold, solid rock accelerates them. By deploying hundreds of seismometers across the Yellowstone region and measuring the precise arrival times of waves from distant earthquakes, geologists compute a three-dimensional map of the subsurface. That map reveals two distinct magma bodies beneath the park, a shallow rhyolitic reservoir and a deeper basaltic chamber. The shallow reservoir is currently between 5 and 15% liquid melt, mostly crystallized rock with pockets of magma distributed through it. Yellowstone is routinely described in popular media as overdue for an eruption. This description is geologically incoherent, and understanding why it is wrong is as important as understanding what actually happened 631,000 years ago. The overdue narrative rests on a simple arithmetic error. Yellowstone has produced 3 major caldera-forming eruptions: 2.1 million years ago, 1.3 million years ago, and 631,000 years ago. The intervals between them are approximately 800,000 years and 670,000 years, respectively. The current interval is 631,000 years, which falls within the range of previous intervals. This is not evidence of a system that is late. It is evidence of a system that operates on timescales that make human intuitions about scheduling irrelevant. More fundamentally, volcanoes are not mechanisms that accumulate obligation over time. They erupt when physical conditions are met, when a sufficient volume of eruptible liquid magma has accumulated, when the pressure in the system exceeds the structural strength of the overlying crust, and when a triggering mechanism provides the initial breach. None of those conditions are currently present beneath Yellowstone. The shallow rhyolitic reservoir is 85 to 95% crystallized. A super eruption requires a reservoir dominated by mobile liquid magma. Building that from the current state would take an enormous amount of geological time and would be accompanied by warning signals of a completely different scale from anything observed today. Those warning signals would be unmissable. Ground deformation at Yellowstone is measured continuously using GPS sensors accurate to the millimeter. The ground above the caldera regularly rises and falls by inches as hydrothermal fluids and shallow magma bodies shift. These cycles have been measured and understood for decades. A genuine magma accumulation event driving toward eruption would produce sustained, accelerating uplift measured not in inches but in feet, over years or decades, accompanied by escalating earthquake swarms as the crust fractured under expanding pressure. The hydrothermal system, the geysers, hot springs, mud pots, and fumaroles that constitute Yellowstone's surface spectacle is not incidental to the volcanic system. It is a pressure relief mechanism. Groundwater percolates down through fractures in the rock, contacts the heat radiating from the shallow magma body, and flashes to steam. That steam and superheated water carry heat and dissolved gases back to the surface continuously. Old Faithful is not a symptom of danger, it is a safety valve. The constant transfer of thermal energy and volatile gases through the hydrothermal system means the shallow reservoir is perpetually venting a portion of the pressure that might otherwise build. The Yellowstone Volcano Observatory, a consortium of the U.S. Geological Survey, universities, and state geological agencies, operates a continuous monitoring network across the park and surrounding region. Hundreds of seismometers record every tremor. GPS arrays track ground deformation in real time. Gas sampling stations at major hydrothermal features monitor the chemical composition of emitted gases for changes that might indicate shifts in deep magma activity. The monitoring infrastructure exists because the hazard is real, not because an eruption is imminent, but because the system is active and will remain so for as long as the North American plate continues its slow drift over the mantle plume below. That drift has not stopped. The hotspot is still burning. The plate is still moving southwest at roughly an inch per year. In geological time, Yellowstone's current position above the plume is temporary. The hotspot's track will continue northeast, and eventually a different landscape will sit above the same engine that produced the Lava Creek eruption. The Lava Creek tuff is still in the ground across half a continent. The sanidine crystals in that ash still hold the argon that accumulated in the 631,000 years since they cooled. The caldera floor is still rising and falling with the breath of the hydrothermal system. The monster has not gone anywhere. It is simply between events, doing exactly what it has always done, building pressure in the only way its physics allow, on a timescale that makes the entire span of human civilization look like an afternoon.